Hey everyone, how's it going? Welcome to my stream. Sorry for the delay. I came down here and wanted to get ready and then saw that Windows 10 had installed updates, rebooted my machine, and nothing was working anymore. My OBS settings, camera, everything was not working, so I had to fix things, reboot a couple more times. Anyway. So finally got everything up and running, hopefully. Just checking here on OBS, everything looks okay. So yeah. So those of you who have been following Ferris for the last, since last Thursday? Yeah, since last Thursday. This guy is really awesome if you're not following him. He's another EmuDev streamer. And he, last Thursday, from Thursday to Sunday, streamed every day and was basically working on getting a teensy to be able to communicate between his PC via USB to his Virtual Boy. So he was doing a whole bunch of serial programming and stuff. Oh, and look at that, he's actually hosting me. But yeah, so if you guys haven't checked him out or are not following him, definitely do so. This guy is really great, has lots of cool stuff, and the last few days when I think he streamed 15-16 hours worth of developing this serial protocol thing. Really fun, really interesting stuff. So definitely check that out. Also wanted to call this out. So since my last stream, I got this issue that was open on the Vectrexy GitHub page by this guy Benji, whose real name is Ben Smith. Basically, he pointed out he was started watching my episodes on YouTube, and just from the very first video saw that I had made a mistake in calculating the overflow flag in the arithmetic shift left operation. You can kind of see it here. And he was pointing out that basically what I was doing to calculate overflow was the idea is looking at the top two bits, right? Bits 6 and 7. We know that if you shift left, overflow would mean that shifting left would cause a sign change, right? So basically, let me bring up a notepad here. So let's say you have something like this, right? So if you shift this left, then that's fine, right? Because this is a negative number, and then if we shift left once, this is still negative, right? So this is good. But the bad cases happen, for example, if you have 1, 0, because then when you shift left here, this becomes all 0. So it means that this went from being a negative number to a positive, or, well, anyway, negative 0. But let's say like this. And if you had this, it's also a bad case, right? Where it's 0, 1, because then this went from being a positive number to a negative number. Once again, we can put a 1 here, because you'd end up with this. Hey, Chief Detector, thanks for the follow. And then finally, a case that's fine would be something like this, right? Where the positive value remains a positive value. Anyway, so the problematic cases are here, and what I did to check that was shift, take this bit, shift it to the right into the first position, take this bit, shift it to the right in the first position, and then do an XOR on it. And basically, if the XOR returns 1, it means one of those bits is set, and we're in the troublesome situation. Except that, as Benji was remarking here, I was shifting right by 6, but I was not masking off the bit in position 1 here, which meant that in the specific case here, I would get this wrong, because I would take the two 1s here, and when I would shift this here to the right by 6. That would give me like this, right? And taking this, let me move this down here. So this is the shifting right by 6. Shifting right by 7 would give me, right? And then of course, if I XOR this, I'm interested in in the bits here in position 0, but this guy here ends up remaining there and giving me a 1. So then I get the wrong result, because I'm supposed to get 0 in this case, right? This XOR this should give me 0, but with a 1 here, I'm gonna get as an overall result non-zero. which is bad. So I fixed it. I think you can see the thing here. Yeah, so there's the fix. I just masked off. I masked in just the bit in position 1. So that should be good. So thank you to Ben. And actually, I've been contacting, like we've been kind of chatting a little bit, and Ben is also an emu developer. He has his own GitHub here. Apparently he works for Google on Chromium. So some cool stuff there. And he's basically implemented BinGB, which is a Game Boy emulator, which looks actually like a really cool project. So definitely worth checking this out. He has also some nice articles on his website about that, and like on his blog here, bing.github.io. And he also started streaming on Twitch here. So that's Twitch TV, Binjimin, Binjimin. He started basically developing a Casio Loopy emulator. And I had no idea what a Casio Loopy is, but turns out it's this Japanese-only console that was released in '95. And what was unique about it is that it was marketed completely, like the marketing for it was completely targeted to female gamers. So, I mean, I never heard about it, but it sounds like a cool system. So if you're, interested in following more emu developers, I recommend you check Ben Smith out, Benjamin out, because there are not too many of us developing emulators, so we got to support each other, right? All right, so that's a bit of news. So, what am I going to be working on? So what I would like to keep doing is I'd like to keep working on what I started the last couple streams. I'm just going to open Visual Studio. Everything is taking a little longer since I just rebooted. Hey Benjamin, look at that. You're actually here. I don't know if you caught me, I just shared a couple things from you. Benjamin says, yo, first time watching live. Welcome to the stream. So yeah, I just hopefully sent you a couple people, maybe people who will watch my YouTube, the VODs later. Okay. So yeah, look, this is where I fixed the bug that Benjamin pointed out. All right. I gotta open all my applications here. I think I made one small change also. Oh yeah. So since last stream, I actually had mentioned this on stream that I wanted to be able to. Okay, so yeah, let me start from a bit earlier than that. So what I did the last couple streams is I worked on improving my trace output. So what I was doing formerly was every time I would execute an instruction, if trace was enabled, I would format the. I would immediately effectively printf a bunch of information to the console. And even with buffering and stuff, it was just extremely slow. We actually took a look in using the Visual Studio's profiler, and we were able to see that most of the time was just spent doing formatting, printf style formatting. It was just crazy how much processing power goes into that, right? And this was happening per instruction. And so basically I was down to what I would do is I would just disable trace and then only enable it when I was trying to debug something. But that was fine for when I started developing the emulator, and most problems would be caught in the first 100 frames or so. But now that the emulator is further ahead, it's becoming more difficult to make use of that. So what I wanted to do, and what I've been working on, is to improve the trace. And so what I did is I rather than doing the printf formatting for every instruction, now I just store a bit of information for each instruction. I'll show it here. So here's the execute instruction, and basically I have this this trace info. So I have this pre-op and post-op trace info that I write instruction trace info here. And what I do is I store the instruction, the state of the CPU registers before and after we execute the instruction, and how many cycles have elapsed, right? Oh, hey, ABD, how's it going? So I store all this, and this is just a little, like a little, struct of data, and I store this in a circular buffer. I think I have like 100,000 of these right now. And I could totally make that larger. Yeah, here we go. So here's my instruction trace buffer, and I just keep, adding into there, and it just keeps cycling. And then if I break in my debugger, I can ask it to show me, say, the last, whatever, 1,000 instructions. And one of the things that I wanted working last week was that if, let's say, an exception occurs, like something, an op that I haven't implemented yet, or more importantly, something goes wrong, like an out of bounds access, I wanted to be able to then show the instruction trace, including the instruction that failed me. And last time that didn't work. And the reason it didn't work is because when I would be executing my instruction, I had this like, pre and post op thing that I was doing. So actually I'll show you that here. Execute. I was doing the pre, then I would execute the instruction here, and then I would wait until the post to add it to the instruction trace buffer. But of course, if an exception gets thrown during the execute, I come out of this and catch it, and I never got a chance to add it. And I mentioned wanting to fix this last time, and so that's what I did. What I did is I wrote a cute little scoped exit RY class. Maybe it'll be easier to show it in code here. And then basically the way it works is it's a templated class where you give it a function, usually a lambda. It gets stored, and then in the destructor it just invokes it. So basically when the thing is, the scoped exit instance gets destroyed, it actually invokes whatever function you constructed it with. And I have a little make scoped exit, and this is mainly for C++ 14 and earlier. In 17, we can actually construct classes now, template classes, without specifying the template type anymore. It will be able to deduce it for constructors. Unfortunately, Visual Studio hasn't implemented that yet. I think Clang and GCC has it, but not Visual Studio yet. So that's coming. So in the meantime, basically my execute instruction now looks like this. So we start, and there's my trace info on the stack. If trace is enabled, we do this pre-op write trace info. So that's where I start to fill in the data structure with the instruction we're about to execute, the state of the registers, and memory bus. Well, we'll get to that. Then I have here elapsed cycles, and then here we go. In case exception is thrown, below we still want to add the current instruction trace info, so wrap the call in a scoped exit. So here we call make scoped exit, and we store it in a stack variable. And the code here basically says if trace is enabled. I guess in fact I could wrap this. No, actually no, I can't. Yeah, so if trace is enabled, go ahead and do the post-op write trace info, and then push it back into our thing. So this gets constructed. It doesn't actually execute yet. Does this, and then when we return, it goes ahead and runs this code. So that's actually perfectly fine. And yeah, if an exception gets thrown during the execute, it also adds what we want. So to show you that this works and how it works, I need to choose a, I think we saw clean sweep was one that would throw. So here's like an example of how this could be useful. All right, so we start our emulator.
At a young age, cooking with kerosene, pan-fried apple green recipes and magazines.
So in clean sweep, we get up until the title screen, where you can choose how many players and all that. And then at this point, if I were to try to play, we get this exception, right? I get an out of range invalid vector subscript thing. So if I hit F5, and we come back to our here, we're broken into the debugger because we caught the exception. But if I say show me the last 10 instructions, actually just trying to show the last 10 instructions ends up causing the same memory read, which causes the same exception, but that's fine. And here we see these are the last 10 instructions, and the one that caused us the problem is this last one here at 0CDC. This load A x, x plus, which means load into A what's in x and then increment x. Well, this is causing an invalid read. So yeah, that's pretty interesting. Now, this part here is what I want to work on tonight, hopefully. Also interesting to note that it says 0 cycles executed, because that's actually what did happen. We didn't really finish this instruction, right? So yeah, no problem, Benjamin. Like I said, we gotta support each other, right? Benjamin actually was saying on Twitter that he wanted to stream at different times to like maximize MU dev streamer time on Twitch, which I think is pretty cool. So yeah, so this is cool. So yeah, the part here about the comments is this is really cool and very useful for me, except that right now it's no longer valid. And the reason why it's not valid is that it used to be fine where by instruction I would go and like read from memory. I would read like at this moment in memory, at this moment that we're executing this instruction, what are the values in memory so that I can show them here. But the problem now is that I'm no longer doing that. I'm just collecting instructions, and then wherever I break, if I say trace and show me the last 10 instructions, we only get to read the values in memory at this moment, which means it's not what was in memory at the time the instruction executed, right? So that makes this a lot less useful to me. So I'm not 100% sure how I want to solve it. I had like a few ideas I was thinking about. Kind of wanted to look at it here. Like I'm thinking something like, if we just look a little bit at how I do this. So it all starts in, where is the function? I think it's this one here. Yeah, disassemble op. So like this is the function that I'm calling over here when I do print op. So to print an operation, right? I'm giving it the trace info, the memory bus. I also have the symbol table thing, which that totally should work fine. But right now we're interested in the memory bus part of it. This function gets called to do this disassembly, given an instruction trace info. And what I do is, I go and I say, all right, what instruction are we going to disassemble? What are the CPU registers? And I'm interested in actually the pre-op CPU registers. I grab the CPU op from the instruction, the address of the op, and that comes from what the program counter was before the instruction executed. And then I go and I do the output of the instruction in hex, so that's totally fine, right? So here we read where, from memory what the what the instruction looks like in hex, and this is fine. And then we have this section here where we disassemble the instruction, and we also are going to produce a comment, and that's the part I want to look at. So the disassemble instruction string, this is like the the human readable mnemonic and the basically the assembly form, and not in hex, right? And I have a couple of special cases here. First, if we have instruction specific handler, these are for special cases where the default addressing mode handlers don't give enough information. Yeah, I'm wondering if I'm going to be able to really take advantage of this anymore. I might have to kind of like give up a little bit on this extra information that I was getting, since I'm like no longer doing this per instruction, But anyways, let's just keep going. So the usual case is I fall over here, because yeah, here I had exchange and transfer, and then I had the push and pull for stack stuff. Now, if no instruction specific handler, we disassemble based on addressing mode. So yeah, basically inherent, that's easy. All we do is we have no comment for inherent mode. Those are simple instructions. Immediate is also fine because immediate means that the value that we want to show in the comment is part of the instruction itself. There's no actual, you can see there's no reads or writes being done. No writes. There's no reads being done from the address bus in here. But when it starts to get more complex is here. For example, in extended mode, we basically form a 16-bit or 2-byte address. So we combine the next 2 bytes here to form the 2-byte address. And then here I had this where I was showing the instruction, and then I was saying, you know, %s, then the effective address that we computed. So right, because that's, so for extended mode, the form is always the name of the operation, the instruction, followed by, say, $, and then the 2-byte address. So that's fine, but then this is the part. For the comment section, here we just try to read from the memory bus, and this here doesn't work at this moment, right? Because that value may have changed or whatever. Like, we're reading the last value there. Okay, so that's one, you know, potential problem. Okay. Similarly for direct, we have another issue here for direct. Direct means that we use the DP register, so the direct page register, plus an offset, which is basically from the program counter. Is that how this works again? I'm trying to remember. DP and... oh yeah, well, we say program counter. It's where the program counter is at the moment we execute the instruction. So basically, it's DP plus a offset that's specified in the instruction, a 1-byte offset. So this allows us to these direct mode is saying our memory is segmented into pages of 256 bytes. We specify which page and what offset into the page, right? So that's and in fact, we don't specify which page in this op. It's just a register. So we set up the DP once, and then after that, all direct mode instructions just specify 1-byte offset into whatever the current page is. So that's the advantage of using this mode, is that if you're going to be doing a lot of operations within one page of memory or whatever, you just set your DP once, and then you just do all your operations, and they take very little space. So this again falls into the same case as earlier, where we are trying to do a memory bus read here. Indexed mode is one of the most complicated ones. I have a separate function for that. This one definitely has memory bus reads in it. In fact, it can have multiple, because if the indexed mode is a indirect instruction, we basically form a 16 once again like a 2-byte address here as our effective address. So this is like a double thing, right? We've already formed an effective address, and then we read from it to get another effective address. This is like the dereferencing a pointer, so the supporting indirect here. And then after that, we once again read from there. So there can be, well, there's only really one read in here. Yeah. Does this make sense? No, sorry, no. That's it. It's right in front of my face here. Basically, when we do index mode, we may be doing 2 reads here and then yet another read here. So up to 3 reads, basically. So that's another thing here to worry about. We just go back. So that's indexed mode. Relative branch instruction with 8 or 16-bit signed relative offset. So these are the relative mode instructions. Let's see here. Try to remind myself what this is about. get, okay, so we have the offset that's actually either in 1 byte or 8 or 16-bit signed relative. Okay, right. That's what this is. Okay, and then this here could be a long branch, page 0 or page 1, 4 bytes, right? Anyway, this is basically we read 1 byte as an offset, or we read 2 bytes as an offset. But in this case, I don't actually read from memory. I just show what the offset's going to be. So yeah, that's fine. We can see that no memory bus is involved here, and then after that, there's a legal invariant, and then there's no memory reads from there. Okay, so basically those are all the problematic ones here that I've identified. So what do we do? So what I was thinking was something like, for each instruction, we can store like in just in terms of utility, right? Like I would have to kind of, let's say, maybe abandon all this nice formatting I'm doing right now for the comments, potentially. And then when we disassemble, if the instruction has an effective address that was stored for it, what we do is we could store the address and the value at that address. And so, like, depending on the instruction, we say, okay, does this instruction actually, you know, need a read from memory? And we just basically go with the final effective address. If so, we store that, and we immediately read the value there and store that as well into our instruction. So that does mean that we increase the overhead, and you know, hopefully it's not going to be too bad. It does mean we're doing extra reads. Like I don't think it's so bad. I think, like, you know, not every instruction will be doing reads from memory or writes there, but like not every instruction hits memory. But when it does, we'll be doing it like double, because we want to store this information in our trace. I think it's fine. I think really what dwarfed the time was the formatting, so I think it should be okay. So we could do that. I'd also like to store whether or not we want to show a 1 byte or 2 byte value, right? In which case, like for the 2 byte values, it means we'd have to do 2 reads from memory. So like that's one way to go about it. Another way, in terms of like implementation, I was wondering how bad it would be, because I already have, like, if we go to the memory bus here, I already have these like callbacks, which actually are pretty horrible. But I was wondering if it would be smart to kind of snoop on the memory bus for trace information, right? And like when an instruction tries to write or read from memory, that also goes and says, okay, you know, we know we're doing this for the current instruction and trace is enabled, so take that address and take the value we've already read. So we save our time on doing the read, although for writes we'd have to do a read anyway. So maybe for those instructions we've read, we can avoid the read, and then add that to the current instruction trace. So that's maybe simplifies. It would definitely simplify what I have to do, because I can just kind of rely on the fact that the instruction is going to hit RAM, and if it does, then we do the thing, we add it. The only thing I'm not too happy about there is the callback overhead, which isn't 0. Like right now I have, let me see here, on read callback. Yeah, see, like I have this callbacks enabled business, which is true. I'm trying to remember, did I disable the callback stuff? Register callbacks. See, like right now, you know, if this is working the way I think it is, we're getting, it's possible we're not hitting this because this is in release. Let me disable optimization. Can I do that here? Optimize off and optimize on here. See if that works. I have these nice little macros to disable optimization for a function, which allows me to debug stuff and still remain in faster release mode. Okay, so yeah. Let's see here. You can, yeah, exactly. So for every execute instruction, I'm already getting called back, you see? So I already have this information. See, so like this would be a place like, and you know, currently I'm checking if there's breakpoints. And in fact, I had to put this hack inside the breakpoint manager to say, you know, temporary optimization to make debug builds faster when no breakpoints have been added. I check if we have no breakpoints, we immediately return, which means that as soon as I set a breakpoint, this code just gets slower. But it's still fast enough in release that it works fine. So yeah, I could basically take advantage of this, right? When we're reading, so the first one is the read and the next one is the write. When we're reading, well, you know, we, do I actually get the value here? This is, okay, so this is write, this is read. Yeah, so this actually happens before we read. On read callback, and then we do the read. So I don't have a callback with the red value. That's interesting, actually. What would be the effect of performing the read? Like normally when we want to hit breakpoints, like normally if you're looking for a watch point on an address, you want to know, you kind of want to break before the read occurs, right? Although I don't think I actually stop the read from occurring anyway. I just set break into debugger here. I say watch point hit, and then after that we go ahead and we do the read anyway. So actually, that's true, I could just move this to after we've done the read, and I can even pass the value we've read. That could be kind of useful, right? Yeah. And actually, I was saying earlier, when we write, I was saying, when I was thinking out loud, I was like, oh, and we'll have to read, but we don't really need to read unless we wanted to know what the value was before we wrote there. But let's say we don't. We just say, well, we're about to write this value, so we'll just report that's the value that's going to be in memory as a result of this instruction. And I think that's perfectly fine. Yeah, I kind of like that. Yeah, I think I was thinking like, you know, normally when you said, let's say, a hardware breakpoint in a debugger, like a watch point on an address, let's say for read, you'd want it to break on the moment the read occurs and not like after. But I don't support that anyway in my debugger, and that's fine. I don't really care. So like what we could do here is we'll change this, right? We'll say value is equal to this. This is the value that we just read, and we'll pass that here in the onRead callback. So this means we need to change our onRead callback definition to accept uint ht, the value this way. Okay. And I wonder if for right I should do the same. I'll leave it alone for now. Okay, so if I do that, that means that this guy here now can have a uint8t value here, and in fact can say red value. So it's even more useful in terms of watch points. So let's say let's just make sure this works. I'll do a little test. Yeah, first I'll make sure it compiles. Why am I getting all these warnings? Oh, yeah. I want to actually return the value here. So yeah, a lot of thinking out loud here on stream, but I haven't really thought too much about it, so. Alright, so let's say I was to break. So like, for example, reading on the dude register, right? So if I say, how's it again? Break, watch, so read, read on dude. That's not how it works. Oh, it's R watch. That's it, R watch. Added watch point at dude. We just continue, and then it says watch point hit, and it says it twice actually. Why does it say twice? Does that make sense? Okay, so we're here, we're reading. Oh, it might be happening twice because of the comment actually. So this would be the first time. This is when we're actually doing the execute instruction here. We're going ahead and reading. We're reading here, we're reading, and then that calls the callback. And if I hit F5, oh, this time it only said once. Interesting. Why did we get it twice? Now I'm only ever hitting it once. But see, it's kind of cool to see the red value. Now we know that when this instruction hit, we just read this value. And if I do this, yeah, there's a few things I have to do there. Right now when I'm doing my, showing my trace, why does it say it's actually hitting it? Oh yeah, because exactly. My trace is causing these watch points to occur, which is a bit strange because I thought I had disabled that. Let me see. Bus. Set callbacks enabled. Oh, right. So I disable callbacks when I populate the trace, but I also need to disable the callbacks for when I show the trace. Yeah, this is a bit of a mess right now. But okay, and that explains why we were getting it twice actually. Now that I think about it. So if I go to get my T here, yeah, basically when I do print op, and I say trace enabled, I'd want to do this here. Is this not valid here? Oh yeah, this is a pointer. Again, this is going to be cleaned up. Because effectively when we do the print op, we will no longer read. That's my goal. My goal is that when we print the op, we've already done the reading of the values, so which is going to be printing at that moment. So again, if I say rwatch on the dude register, okay, and then we hit it this way, and if I say trace 10, okay, now we no longer get it, despite the fact that we can see that in the last 10 instructions, every second one was a read from dude here. Okay, so yeah, I think we have a plan. Yeah, take off this optimize thing. Oh, it's this function up here. So Benjamin says, might be simpler if you had a raw read function that bypasses callbacks and never throws. Yeah, I've thought about that. I have thought about that. It's just that if I do that, I need to kind of, implement that everywhere right now where I have potential memory reads. So, I've also thought about along similar lines, like having read and write kind of take a parameter. Is this a raw read or not? Because the way it works right now is I have this memory bus, and on the memory bus I have a bunch of devices. And basically we have this device info struct here where I store each device in the memory range that it covers, and then basically the memory device implements read and write. So, and I have a few of these, right? I have the BIOS ROM, the cartridge, RAM, unmapped memory device, and the VIA. So I have 5, 6, something, 1, 2, 3. 5, 6, anyway. So, I'd have to kind of duplicate my logic, but at the same time, it's not, I might actually have to do something like that because some of these reads and writes have side effects. And I'm not actually right now not taking care of that, and I'm probably it's gonna bite me in the ass if it hasn't already. Like for example, in the VIA, do I have a read that causes side effects? I might. Trying to remember, I think I did. Anyway, if I do, this is not good, right? I'm not sure if I do though. I don't yet. That's it. I don't have yet a read with side effect, but the moment I do, this kind of thing is not going to work, and I will want to have some kind of special, like you say, a raw read that says just get the value but don't do any kind of side effects. And at that point, I probably will just be passing a flag down to the write and read and have special handling for it. I think that's what I did in my NES emulator. So, and yeah, I guess I could use that as well. That would be used as well to say don't bother calling callbacks. But then again, I do want to call them for watch points, So we'll see. Okay, so let's do this. Let's go to the instruction trace info. Benjamin says, makes sense, easier than plumbing through and duplicating those functions. Yeah, I think so. And since I haven't needed it just yet, I haven't done it, but the moment I implement, and I know there's going to be, I think there's some functions in the VIA related to sound and stuff like that, where you read values and it's a shift register, so every read actually changes the value. So once I have that, I'm going to definitely need a special mode for reading for the debugger without modifying the value there. Okay, so I want to store address value pairs, I suppose. And I'm thinking, trying to think, like, I think at most an instruction will do like at most 2 reads. Like for example, those indirect ones, right? There'll be a read to get the address and then another read at that effective address. So it'll be, yeah. And then I'm thinking in terms of, there's a bit of information I need to encode there. So there's the address, and then there's the value, and the value can be a 1 or 2 bytes. I also need to know how many of those I have. It's a bit tricky. Actually, I guess for the 1 or 2 byte, I don't really need to care. I can just store a 2 byte value and, you know, print it as just a value, and we'll, you know, it'll show whether it's a 1 or 2 bytes, I suppose. I don't know. Do I care? Do I want to know? I'm not sure. Okay, let's see. I don't know what to call this. And I need something to store here, so like an address. And for now, I'll do an UN16T value, and we'll see if we care about knowing whether it's 1 or 2 bytes. One thing I wish was, one thing I don't, you know, I like std array because, okay, wait, it doesn't like this. All right. So I like std array because, you know, it's fixed in size and all that. What I wish that it offered was, I would like to have like a std array that's like vector in that when you create it, it has a fixed size and you can't surpass it, but its size returns 0, and that you can push back values, and it just has an internal counter that increases. And let's say like it, if it ever, you know, overflows, it would throw or something like that. Because I always find myself having to like keep a separate count. And when I worked at EA, we had the EA STL, and they had a type like that. I think they called it fixed vector. That was more like what I wanted. It allowed you to have this fixed size, and I think it even had a policy for like if you'd run out of you know, if you surpass your buffer, what do you want to do? Do you want to like assert hard or fail hard, or do you want to now go to the heap, right? So that was really kind of flexible because you could get the best of both worlds. Anyway, a bit of a rant, but so let's say I have this. Put that here on screen. Benjamin says, haha, I worked at EA too. Oh yeah, no kidding. That's cool. So you know about EA STL, I suppose? I mean, it's partially open source, right? Like people wanna, if you look up EA STL, Paul Pedriana is the main author. He's a guy who, he now works at Oculus, but he was working at Maxis, and EA bought Maxis, and so then they they got his STL library that he wrote for games. But yeah, it's this thing here. So I wonder if it has it in here, actually, now that I'm mentioning it. Fixed vector. There it is. This file implements a vector which uses a fixed size memory pool. The beat enable overflow template parameter allows the container to resort to heap allocations if the memory pool is exhausted. So that's exactly what I was talking about. Yeah, Benjamin says, yep, we didn't really use it on our team. You know what? This was one of my favorite things about working at EA, was being able to use EA STL. The one we had at EA was actually fuller than this one and had way more options. I think the one that was open source was like a narrower version. I'm not quite sure why. Maybe it just needed to be vetted or something. But yeah, it was great. We used it for everything. All right. Okay, so now one thing is that the trace info that we're building on the stack here is the thing that I want to modify in those callbacks. Okay, so in that case, what we're going to do is I have two choices. I can either add it to my trace buffer and then read it back in order to modify it, which I don't really like. Or I can just have like a pointer on the current instruction trace info, which should be okay. Should be okay. Let's do that. And for now, since I did not expose any of this into the header, I'm going to have to make it a global. What is it? Like this. If trace is enabled, it'll get set this way. And when we're done, we'll just reset it to null. And now that we have the scoped exit, I know this code will always be called, so we should be okay. All right, and now we go into the callback. Here. So if trace enabled, no. So this should be set. Now. Okay, you know what I'm gonna do is I'm gonna 642 is up here. I'm gonna go to, I'm gonna put a little helper function. sure that we fit. And we add that. Okay, plus plus. I guess I can do the plus plus now this way. So that's the add memory value. So we come back here and we say add memory value, address value. And similarly, when we read, we do the same thing. Okay, so now we have that. So now if we go into our disassemble this atom, okay, I'm also noticing that my nice functions for exchange and transfer and push-pull don't even use the memory bus, so that's kind of cool. Because I'm wondering how much of this I can keep in terms of formatting. Just need to kind of rework a little bit the way I do the comment section, and then I can maybe keep some of this. Okay, so what we're going to do, since the idea is not to use the memory bus, we're going to actually remove that as a parameter altogether. Move it here as well. No, actually I do need to keep it here for these reads that I'm doing here, but I don't need it there. Don't need it there. All right. So now I'm seeing how much of this I can keep. There may be some redundancy here, but I think like where I'm commenting out these ones with comment, it's because we know we're going to be doing reads from memory for those, right? So I take those out. think I missed something. Yeah, this is what I missed. In the indexed one here, I actually do need to pass in. Do I need to pass it in? No, okay, I don't. Because we will already have stored the indirect address here. Right. Then it means I can't have a nice formatting here for the disassembled instruction. Okay. Actually, technically speaking, this was not really correct, right? I'm showing here the indirect operator here on an address, but the address here is supposed to be EA and EA plus 1, and not the combined, like not the actual dereferenced value. Like I would need to effectively remove these here to show what we're trying to dereference. I'm wondering if I should show EA and EA plus 1 here, because we are going to be doing multiple reads here. Okay, one step at a time. So this should compile. From here, local variables initialized but not referenced. All right. Oh, actually, I could keep at least part of this. Even here, so I mean, there's so many ways I can go about this. I keep thinking like maybe I would like to try to keep the work I did before. A lot of this was helpful, So if I can keep it, I will. Otherwise, I kind of abandon all of this and just say, here are some addresses and values, you know, and figure it out based on the context of the instruction. I should be able to figure it out. But then you know, it's kind of nice to have some of this. So if I can keep most of this work, then I'll try and do that. Like all the special handling and so because the comment section, yeah, it contains information, right? So let's say I did this, and then this is the part where we'll see if the instruction has addresses and values, and we'll show those, we'll append those to comment basically. What was it? Why is my autocomplete not showing it to me? Don't like when my IntelliSense is not working. Just not working. Okay. Alright, so if this is the case, what we want to do is something like something like this. Let's just see what this looks like. Oh, right. Interesting. When we reset the CPU, we actually do a read from FFFE, and at that moment we have not yet initialized the debugger, and therefore we don't have our callback set. Does that make sense? Oh no, we do have our callback set up, but we don't have a pointer on an instruction yet. That's interesting. Because it's not really an instruction. That sucks. So technically, I can't really assert this, even though there's only really one case where, like, this won't be true. Okay, so now what? Oh, similarly. Actually, you know what? Let me run and debug so we hit asserts. I have these asserts that are not even tripping right now. Alright, so we're hitting an assert. Alright, so this is where memory values is not large enough. Does that make sense? Oh, I suppose it does make sense for a 16-byte indexed value where we dereference. See here? Read operand and value 16. Immediate, actually. Read 16 PC. Oh, yeah. Right. Think about that. When we execute an instruction, we do many more reads than just the ones for the operands. We do the reads for the actual instruction as well. Okay, it's okay. Let me just make that buffer larger and then let's see what we get. Here, let's just make this 10. Make it comfortably large, and we'll see how it goes. Okay. So yeah. So there's the first read here is always going to be the instruction itself, right? It's like F1A0. And then I guess the next one is actually the value we care about here. Right, and then this one here had two F19E, F19F for the operand, and then the actual thing we care about. it makes sense. I mean, basically, when we execute an instruction, we there is a bunch of reads that we do right off the bat, right? Like we read the first byte for the opcode. We might read another one if it's a page 1 or page 2, so that's potentially 2 bytes for the opcode. And then after that, it depends, right? And for like immediate mode, we're reading the next byte just to get the value, for example, that we want for the immediate mode instruction. And I'm just basically recording all of those reads right now. And I don't really have a way to know. I mean, technically, I guess I could know, you know, we know which address range would be instructions. So I could skip any address that falls into the, you know, the code sections. That's a possibility. Like if we look at our memory map here. So we know that yeah, so we have cartridge ROM here. So anything that falls inside there would be basically an actual operation. So we could technically skip all of that. There's also kind of a special case for Mindstorm, where when we're running Mindstorm, we'd want to skip, I guess, the first half here where it's Mindstorm's program running. There's also the question of whether we want to skip the BIOS, because those are instructions as well. Or maybe it's the other way around, right? We only care about addresses that fall into RAM. Maybe that's the right way to go about it. We filter in addresses that fall into RAM. Well, RAM, and I guess via this range here. Let's see. So let's say if we have a memory map here, memory map. I don't think I have a way to query a range right now. But mapping, first, last, and it sets a physical size, logical size, sets a range. I have a map address function, but I haven't. Oh, I have it is in range. Make a little helper here. Benjamin asks, does the Vectrex ever execute from RAM? Game Boy does that sometimes, like when doing DMA. I don't believe so, no. There's very limited RAM. I don't think, I mean, I could be wrong, but I don't think there are any programs that are actually executing code out of RAM. There's just so much more ROM space, and there is some cards that are doing bank switching, but I doubt it so much that they'd actually run out of this very small amount of space here. Like, basically in RAM, there is 874 bytes that a programmer can use. And that actually includes the system stack. So it's even less. So I don't think it's likely, but I see your point. I mean, if it did execute out of RAM, then filtering here would mean that we'd lose, important information. Oh, that's true. I did not include. Where does pair come from? Oh. I think that's... Why is this underlined here? Oh, because it doesn't know which is in range I'm calling. Do this, right? Yeah, looks like I can. No, okay, it's not global. Yeah, Benjamin says, wow, pretty tiny. Yeah, I know. It's extremely limited RAM. So it looks like I could get away with this strategy for now. We'll see, we'll see. So, sorry, not memory map. So if memory map, and then we say RAM is in range. Oh, I guess I gotta make it, what do I want to do here? No, it's actually an instance. It's, oh, sorry, yeah. Dot is in range. Address. Oh, that's cool. So here we have a subtract D C8 C8 to C. So we're saying read the values, the two bytes basically. So we get F1 and 30, and subtract. Forget the direction. Okay, so it's A minus B. So it's basically register. So take the value in D and subtract the value in memory. I think that's what it means. And store it in D. Yeah. Let's see if that makes sense. So when we call this, D had 000D, then afterwards it will have 0, 0, 0, B. Does that make sense? Okay, so D is both A and B combined, so 0, 0, 0, D. And apparently we're subtracting F130. It's been so long I haven't like thought about this. You know what, let's just try a different instruction. Just look at a few more examples here. So here's our return to subroutine, F329, and that is indeed what we go to, so that's interesting. Store B -1 S, -1 CBE4. What is the stack pointer here? It is CBE4. So why would we have read from CBE3? Let me see. Pull S, A, comma, B. The stack is CBE4. Oh, wait a minute. Of course. Because the registers, yeah, right. This is kind of a, yeah, right. The values that I'm showing here in the registers are the values after the instruction has executed. That's why. That's why it looks like this. So for example, here when we pull from the stack two values, 2 bytes, A and B, it's kind of interesting. We see it. It's reading first from CBE2 and then from CBE3, leaving the stack now pointing at CBE4. So actually this makes sense. And it also means that A and B should end up with DF-E9 in them, which is exactly what we see here. And we can see that before that, they were at CE-E9. So pulling from the stack changed, in this case, A, but it wrote both. So that's kind of cool, right? And so that probably explains the other thing I was looking at earlier. Where was it? Here. Store B -1 S. So here, that's right, because what we're doing is we're reading from CBE4 -1, which is CBE3, and getting the value of 17 and storing that into B, which, well, it already had 17 in it, but anyway, it wrote 17 there. And actually, we then OR into A that same value of 17, so we're ORing 17 with 21, and getting 37. Like, I'm wondering, you know, just how much of what I wrote here is useful in general. So like here, load A U plus. So why didn't we get... So that's interesting, right? Like here I have a instruction that would have read from memory. Ah, right. F122. So this is because it's reading from BIOS here, and actually there's going to be a lot of reads from the BIOS that we're not going to see. And it's static, but yeah, it's kind of tricky. So the BIOS memory is a mixture of code and data. And so if I include it, then we're going to end up with like every time we jump into BIOS code, and actually all of this is BIOS code. Every time you see F here, we're executing a BIOS function. And so there, sometimes it'll just read data from the BIOS ROM, and we're not going to see the value there. So yeah, it kind of sucks. You know what? I'm gonna get some water. I'll be right back. All right. So I'm wondering if I really care, because the values in ROM are read-only, and I mean, usually we can figure out just by looking at what ends up in registers. For reads, it's really simple. It's really the writes that are more annoying. The reads always end up in a register anyway, right? And we can just look at the value in the register here, and we see what happened. So I think we might be okay with what we have. So like for example here, right, where we're saying load into D, U, what's in U, and then increment U by 2. So if we look at U, it was F124 and it became F126. And we loaded it into D, which means both A and B. So at F124 was FC60. That's what this means. So even without actually seeing what happened, and again, these values don't get modified because it's wrong. So this may be enough for me. Maybe. I don't know if I can think of a better or smarter way to do this. The only other way I can think is I don't use like this memory bus hook. And I kind of like do it, you know, when we are capturing the instruction trace, we look at what instruction it is, and then based on the context of the instruction, we say, oh, this instruction would want to know you know, would read from this address or these two addresses or whatever, and then we go and get those values then and there. But I feel like that's like a lot of processing, or like double the work, in the sense of right now the disassembly function I have, I'd kind of have to duplicate it, and where like the first pass is based on which instruction, figure out which memory we're going to be reading and store the address and values, and then when we disassemble it, then we know that those values have been captured before. So I kind of don't like that. Another way potentially would be to kind of have like a marker, you know, where when we execute the instruction, we know that we're right now reading the bytes that are relevant to the instruction itself. These are instruction bytes, and now I'm reading non-instruction bytes, which is what we would want to store here. So it's kind of like I need to know, is the CPU decoding an instruction versus is it now like reading, you know, values for operands, data and all that. One thing I could do I do have this information that the CPU has in terms of like how many bytes are just the instruction itself, and maybe just skipping those and allowing it to read the rest would be okay. Like what I'm doing here, I do have the CPU op, and like knowing if it's an opcode page 1 or opcode page 2. Well, if it's either one, it's those first 2 bytes I could skip. So if I skip those, but then I end up reading bytes that are like, a lot of instructions just have like another 1 or 2 bytes that are either the immediate value or like an address. Not sure. Let me think here. What can I do with this? CPU off there. Yeah, in fact, I've already encoded that because I know which op page it's on, in fact. So I could even just do that. Interesting. It won't be as clean though, because I need to like skip bytes, right? I'd have to have like a little counter in there. Let me see if I can hack something here. I hate that my IntelliSense is not working here. Benjamin says, agree. Instruction bytes aren't that useful since you can see them on the left. More useful to see other memory accesses. Yeah, that's for sure. So I can skip those. I'm just wondering if we're still gonna get too many addresses. Like showing too many values being decoded from, because there's the part that is the instruction itself, and then there's still the part it's still part of the instruction, right? Like the operand data that I would love to skip. And maybe I can actually, because in my op table, yeah, let me just try this one step at a time. So, oh, there we go. This is working again. That's nice. Oh, this is new. That's cool. Okay, so let's say I take instruction, and so we have the page here. So if it's okay, we'll definitely skip 1 for the instruction plus, and if the page is not 0, then we're going to skip, or if it is 0, then nothing or 1. Wrap this up. This should allow us to skip at least the instruction part, but actually we have more information than that. I was saying we have the CPU op here, and the op has a size. The size actually tells us exactly how many bytes we can skip, including the op. So that's interesting. I do need to take into account the page though, because that's not counted in there. Or is it? Let me check. Maybe it is. Oh, I think it is. So maybe I can just skip that. So if the size is 2, we want to start at 2. Yeah. And we will then remove the filtering we were doing. Now this does mean we end up storing too many values, but I'll worry about that after. So let's remove this filtering that we did earlier. Let's see what this looks like. Okay, that's pretty cool. I'm wondering if this is right. Would I not have expected to see a read from this address? Branch if not equal FA 26 FA, so that's 2 bytes. Oh right, there's no read or write here. I just compute an address and that becomes, so that's correct. Okay. How about this one here? What do we got here? Negate at 0, 1. So that's a direct page instruction. C8. 38C8. I don't even remember exactly what this does. Neg address, neg A or neg B. So it just takes the value, negates it, and then stores it back there. Yeah. Okay, so this is saying reads this the value at this address and it will negate it. 38C8. Store what's in A to 0, 0, so this will store at D0, 0, 0 the value that's in A, which is 1. Yeah. Okay, so here's load A, and you know here we are executing instructions that's accessing the BIOS memory. So we're getting what I wasn't getting before. Here we're loading into A what's at the user stack pointer, and then we're incrementing it, which means we're loading a value that should be at F138. Yeah, and that's 4E, and 4E should be an A. Yeah, there we go. So this is pretty cool. Yeah, I think this is the winner. I think this is the right way to do it. By just skipping the bytes that are instruction bytes, we get the values we want to show. The only thing now is that I'm actually storing all those values. And in order to avoid that, Benjamin says, nice, looks good. Thanks, man. So yeah, like the only bad thing is yeah, Benjamin says might be cool to differentiate between loads and stores. You know, that's a good point. I could totally do that actually, really easily. But before that, one thing I would like to, I wonder if it's worth it. Like right now, I'm just adding memory values for all those ops, you know, like for the bytes that are related to the instruction itself, and it's totally needless, right? And then I go and skip it later. Ideally, I'd want to skip it beforehand, but in order to do that, I'd need to know when I'm adding my value, if I need to skip this one or not, you know? So that's a bit annoying. One way to do that would be like, because right now I'm like setting instruction directly. Like, okay, where is it? In here, in the pre-op trace info, I'm going set the instruction here. At this moment, I could say, oh, and skip this many bytes, and like every future write would skip until there are no more bytes to skip. It's extremely hacky though. But it would avoid, you know, wasting cycles just writing these key value pairs into the array for nothing. I don't know, I wonder how much overhead that really is for me. Like, what would it look like? Gross. Okay, I feel super uncomfortable doing it. Okay, let's do what Benjamin was suggesting. Or whatever. Like this. We say this, and whether it's a read or not. True, and then here it'll be false, because this is right. I should actually say what it is here. On read, on write. Okay, so we do that, and then when we go and write our values here, oh yeah, and I wanted to put a $sign because these are hex values. And oh, you know what would be cute here is something like something like this, you know, where this is like a write and this is a read maybe. Let's see what this looks like. Oh yeah, might be useful to actually store it. Alright, this is pretty cool, right? Does this even make sense? Huh. Yeah, that's really interesting. That's really interesting here. Because here we see like decrementing at 0, 0. So that, you know, that's D000, and there's a read followed by a write. So we read 3 and we decremented it and wrote 2. That's pretty cool. I like that. That's really cool. Great idea, Benjamin. Here negate 0, 1. So here we read 60 and we stored a 0. That makes sense. All right. Yeah, there's a 0. So yeah, it makes sense. Benjamin says, since read writes is so common, you could even try to do clever stuff to compress, like D00 would be $2 to 3. Yeah, for sure. Yeah, like noticing that if the same address is repeated and the values change, just show how, yeah, I could do that, but yeah, like you say, maybe more trouble than it's worth at this point. I think I get quite a bit of information now with this. Maybe the right arrow is a bit strange. I don't know. No, I guess it's like from this address we get this value. The other way around is this value goes to this address. No, I like it. It's good. So yeah, so the only thing that's still bothering me again is the fact that I'm needlessly writing all those bytes in here that I don't need. So I'd like to solve that. In fact, before we even go much further, let's just see how this performs in release. Okay, so here we have a branch subroutine B1. So that basically computes the 0CDC apparently, which is where we're at. And to figure that out, we ended up reading at CBE5 and CBE4. Because, why? Because of that's where program counter was, right? Let's see, program. Oh, we don't. Program counter is here, but that doesn't. Okay, this is writing the return address, isn't it? What is this? 2B and then CBE4. Yeah, this looks like we're writing. What's our stack? Okay, yeah, that's it. We're writing to our stack the return address. But would it be 2BD? It's a bit strange. Maybe that's our bug. Yeah, push 16 to the stack, the current value of the PC. Don't quite understand why I would be pushing 2BD here. 2B0D, let's say. Okay, so this is the 0D. Okay, 29 plus the offset would be 2B. Yeah, okay, that makes sense. This is a 2-byte instruction. So PC plus it includes, so this would be like 29, 20A, 20B, exactly. Okay. Okay, it makes perfect sense. So this basically is the pushing of the return address for where we would be after this instruction. So this makes sense. Okay. Pretty cool. So yeah, last problem. Before I do that, I guess I can just do a bit of one thing also I wanted to try was to see how it combines This might get really noisy, but I still have my path to the symbol file. This here. Let's just get rid of Mindstorm for now. So if we break here and we load symbols, yeah, so we can see that my symbol stuff is working as well in relationship to this. It's a lot more noisy, but it's useful. We can see like here, this dude register is the via int flags. Just gonna go a bit further ahead. So yeah, like stuff like this, via shift register. Port A, port B. Okay, so that all works. I think I'm going to leave it like this for now because it didn't seem to affect performance very much, storing the extra bytes in there, and it just keeps the code simple. And if ever, like, you know, it shows up in a trace or something, I'll worry about it. Because I mean, look, I'm hitting what, around 500 here, average around 500 FPS. So I think even with all the trace we're collecting and stuff, it looks like it's fine. It's interesting how it drops quite a bit when I... Oh, what's this? So it looks like we actually have an instruction here that even surpassed 10. Oh yeah, interesting. So the pull instruction is a really interesting instruction because the pull can pull a bunch of values from the stack. So even 10 is not enough, considering that you can pull up to like 1, 2, 3, 4, and then another 2 bytes here. But anyway, these are still single values. So 1, 2, 3, 4, 5, 6 values, 7 values, 8 values. So you can actually read up to 8 values with one instruction right here, plus the bytes of the instruction. So 10 is not even enough if I'm storing everything, right? That's really interesting though. You don't, I forgot about that. Really powerful instructions in this old architecture. Here, let's choose a nice, happy computer number, 16. Yeah, the frame rate definitely changes based on the size. When I go to full screen like this, I'm at around 188, 180 or something, 190. Then if I go to this size, I'm at 500. And I mean, it makes sense. There's like more work to do, right? So, and I don't have the rendering in a separate thread or anything like that, so. And now if we break, yeah, very cool. Okay, so I'm happy with this. Let's look over the diffs. Benjamin says, whoa, looks really nice. I'm still way behind on YouTube. Very cool to see so much stuff working. Yeah, well, you just started, right? Watching the videos. So it's huge progression from the beginning of when I first started streaming to where I'm at now. But hopefully you'll find it enjoyable to watch. I mean, including all the stumbling that I do here and there. Just part of it, right? I wanted to put a comment here to why we're skipping bytes. Skip. Skip. Only print. Benjamin says, definitely, the process is the most fun part. I agree. It's fun. Skip instruction bytes. Only print. What is I'm trying to say here? Don't show the there we go. Don't show the opcode plus operand bytes. Skip the opcode. code plus operand bytes. And I'll say here to do. We shouldn't be storing these in the first place. Probably shouldn't be storing these in the first place. Okay. Trace enabled. Oh yeah, so we can go clean that up. 649. So if trace is enabled and we have a cur trace info pointer, then we add the read here. We also check our breakpoints. And we write. Do this. I just realize I don't really like this memory value name very much. I think a better name is memory access. I think that's more clear. And this, now I don't really need this, actually. 680. Because print op technically doesn't even need the memory bus. Is that true? No, that's not true. Because it's true, I do need to read. Do I need to read this here? Is this the only place I'm reading from the memory bus? It is, isn't it? Nah, you know what? I should get rid of this. Can then I need to. I think I have this information. Let me see. Yeah, technically I have them stored here. I have the opcode byte because I've read it, but actually I'm consuming it here, and I look it up here. So I guess I could, yeah, I have the, with the CPU op and with my operands, I'm kind of like, now I'm like double reading from memory, so I don't need to do that. One thing is I don't know how many operands I've read. It's like the same problem I keep having. Again, if I had... Maybe I should make like a little wrapper, you know, to do like the fixed vector thing. Because that's what I would want here, you know? Yeah, what's bothering me right now is that I'm passing in the memory bus to the print op just so that I can do this in the disassemble op here. The only reason I need it now is to get this hex instruction, and I actually have this information already. Not as easily accessible as I want, but it's in there. It's part of my instruction. I have the CPU op, so I can get the hex values for the op there, and I have the operands. And I'm wondering if I should just, since I'm already populating the instruction in my read instruction here. See, this is where all the this is what I'm talking about. All of this here is enough, is all the info I need. You know what? I'm gonna do that as another change. I'll just put a to do. And then these lines that enable copy paste bug on top of it. All right. Debugger. Make instruction trace, store, reads, write, store memory accesses, and display them. Display them when showing trace. Push that, and then what I wanted to do is let's do this to do here. So I think the right way to fix this, if I go back to my instruction trace info, instruction, here's what I'm thinking. Here we store a pointer to the CPU op. We're storing a pointer to the page. Why is that again? I think I'm not even using this. I'm storing it though. Okay, I'll just leave it there. And I have the operands. So what I'm thinking here is instead of this, we do You know what? No, we'll do this a little bit differently. We're just gonna go like this. An op is just up to 2 bytes, right? So these will be opcode bytes. And then this will be operands like it was before. I do need to know how many we've added in total though. I keep bumping into the same thing over and over. The fact that I wish I could have a count instead array. This really should just be a pushback and I should just be accessing size. Nah, this doesn't work. I just realized. I'm reading this comment I wrote a while ago about the reason why I read up to 3 bytes. Like I always read 3 bytes worth of operands from memory, even if the instruction doesn't take 3. It may take 1, 2, or 3, right? Or 0 even. And I do it here because I say we would want to only read as many operands as stipulated by the opcode size -1 or 2, if not on page 0. So that's to subtract the number of bytes for the opcode. But unfortunately, indexed instructions sometimes read an extra operand byte, determined dynamically. So for disassembling purposes, we just read 3 bytes and call it a day. And so what this means is I did this because then when I go ahead and disassemble in indexed mode and I determine dynamically, oh, we know we would need an extra byte, I read from that opcode, from that operand, I mean. But what it means is that the hex instruction that I display would be missing a byte in that case, because I am using the size to know how many of those to display. And when I wrote this, I guess it didn't occur to me, but that's what it means. Like, it's like a... But then again, I guess I would have a chance to know now, right? Since I display the instruction after it's executed. So there would be a way for me to know exactly how many bytes this instruction really takes in memory. You know what? I'm gonna stop here. I'm gonna think a little bit about this. I'm not really liking what this is looking like here. Kind of looks like crap. And I'm gonna think a little bit about what I was just saying now. Determining the exact number of bytes to display, or how many bytes exactly this instruction takes, even in the case of indexed mode, and find a more clear way to represent that, if that's possible. Here it's not possible, right? Where I'm doing read instruction, this is like too early because I haven't executed it yet. But after I've executed it, I know exactly, I should know. But how do I get that information back? I can't look at the program counter because a jump instruction, a branch instruction will move the program counter. So I can't like rely on how many, like how far did our program counter move after the instruction, right? So that's not going to help me. But what I could do is I could store like all the bytes, and then when we disassemble, maybe the first step would be to figure out, like collect the data and then do the formatting for the hex instruction afterwards. We could do that. Like over here, disassemble op. Like right now I'm starting and I'm immediately, like I'm formatting into hex instruction here, the bytes for the string based on that size. But like I said, this could be +1. But then I go ahead and you know, in indexed mode here, we do disassemble here. So I could kind of get that information out of here, and we could do the building of the hex instruction afterwards once I know that. So I could fix that. well, I think it's a good spot to stop. I'll be streaming again in a couple nights, like on Wednesday. So we'll just pick up where we are at now. So guys, thanks for watching, and hope to see you in a couple days. Take care.